Hi students, today we are going to see the topic about annealing. Myself Sathish, Assistant Professor Mechanical Department at Akshay College of Engineering and Technology. Annealing is a heat treatment for the general purpose of softening or stress relieving a material. Steel is annealed to reduce the hardness, improve machinability, facilitate cold working, produce a desired microstructure. Full annealing is the process of softening steel by heating and cooling cycle so that it may be bent or cut easily. In annealing, steel is heated above the transformation temperature to form austenite and cooled very slowly, unusually in the furnace. This is a gas torchlight. We are heating a plated metal to make the process of annealing. Annealing. There are several types of annealing like black annealing, box annealing, flame annealing, isothermal annealing, recrystallization annealing, finish annealing, blue annealing, bright annealing, intermediate annealing, process annealing, soft annealing, spheroidized annealing. These are practiced according to the different final product properties in the industries. In general, annealing treatment can be classified into group based on the following: heat temperature, heat treatment temperature, number 2 phase transformation, number 3 specific purpose. In heat treatment temperature, full annealing, partial annealing, subcritical annealing we can see as a group. In phase transformation, first order annealing, second order annealing we can able to see. In specific purpose, we can able to get a specific type of the structures. So here we can see full annealing, isothermal annealing, diffusion annealing, partial annealing, recrystallization annealing, spheroidized annealing. In full annealing, the steel is heated above the critical temperature and then cooled very slowly. Partial annealing, also known as incomplete annealing or intercritical annealing, involves heating of steel to a temperature lying between the lower critical temperature and upper critical temperature. Subcritical annealing is a process in which the maximum temperature to which is heated is always less than the lower critical temperature. Classification based on phase transformation features. First order annealing is performed on steel with the sole aim of achieving some properties. Any change in the characteristics of steel achieved by this type of annealing is not corrected to phase transformation. It can be performed at a wider range of temperature above or below critical temperature. The second order annealing differs from the former in the sense that the end result in the former are essentially due to phase transformation which takes place during the treatment. And types of annealing based on specific purpose. Full annealing. In this annealing, steel is heated to its 50 degrees centigrade above the austenite temperature and held for sufficient time to allow the material to fully form austenite or austenite cementite grain structure. The material is then allowed to cool slowly so that the equilibrium microstructure is obtained. The austeniting temperature is a function of carbon content of the steel and can be generalized as hypoeutectoid steel and eutectoid steel, hypereutectoid steel. Purpose of full annealing: to relieve internal stress, to reduce hardness and increase ductility, for refine of grain size, for making the material having homogeneous chemical composition. For making the material suitable for high machining process. To make steels suitable for undergoing other heat treatment process like hardening, normalizing, etc. Now we are seeing isothermal annealing. It is a process in which hypoeutectoid steel is heated above the upper critical temperature and this temperature is maintained for a time. And then the temperature is brought down below lower critical temperature and is again maintained. Then finally it is cooled at room temperature. The prefix isothermal isolated with annealed implies that transformation of austenite takes place at constant temperature. In this picture we can able to see the closer the temperature of the isothermal holding is to A1, coarser is the perlite, softer is the steel, but longer is the time of isothermal transformation. Advantage: improved machinability, homogeneous structure and better surface finish. Time required for complete cycle is comparably less. The process is of great use for alloy steels as the steels have to be cooled slowly. Limitations: it is suitable only for smaller sized component. Heavy components cannot be subjected to this treatment because it is not possible to cool them rapidly and uniformly to the holding temperature at which transformation occurs. Thus, the structure won't be homogeneous, so mechanical property will vary across the cross section. Diffusion annealing. This process also known as homogenizing annealing is employed to remove any structure non-uniformity like dendrites, columnar grains, and chemical inhomogeneity which promotes brittleness and reduces ductility and toughness of steel. Process: steel is heated sufficiently above the upper critical temperature and held at the temperature for 10 to 20 hours followed by slow cooling. Segregated zones are eliminated and a chemically homogeneous steel is obtained by this treatment as a result of diffusion. Heating to such a high temperature results in considerable coarsening of austenitic grain and heavy scale formation. The coarse austenite thus obtained further transforms to coarse perlite on cooling, which is not a desirable structure as mechanical properties are important. The main aim of homogeneous annealing is to make the composition uniform, that is to remove chemical heterogeneity. The impact energy and ductility of the steel increases as homogenizing temperature increases and hardness, yield strength and tensile strength decreases with an increase in the homogenizing temperature. Homogenizing annealing has a few shortcomings as well. It results in grain coarsing of austenite, thereby imparting the properties. Thick scale on the surface of steel. It is an inexpensive process. Now we are seeing partial annealing. Partial annealing, also known as intercritical annealing or incomplete annealing, is a process in which steel is heated between A1 and ACM and is followed by slow cooling. Generally, hypereutectoid steels are subjected to this treatment. The resultant microstructure consists of fine perlite and cementite instead of coarse perlite and a network of cementite at grain boundaries. As lower temperature are involved in this process, it is less expensive than pull annealing. Hypoelectric steels are subjected to this treatment to improve machinability. However, steels are core structure of ferrite and perlite are not suitable for this treatment. This is because only a considerable amount of ferrite remains untransformed and only a part of it along with perlite transforms to austenite. This cause or acicular untransformed perlite structure is poor mechanical property. Now we are seeing the topic recrystallization annealing. The process consists of heating steel above the recrystallization temperature, holding at this temperature and cooling thereafter. It is used to treat work-hardened part made out of low carbon steel, less than 0.25% of the carbon content. This allows the part to be soft enough to undergo further cold working without fracturing. Now we can see an image as an example. Here we can see different processed annealing. The different structures of the temperatures varies gives a processed annealing, spheroidized annealing, case refining, normalized and hardening annealing, ferrite pit austenite structures of the different formations we can able to get when the carbon percentages vary. Recrystallization temperature is given Tr is equal to 0.3 to 0.5 temperature. As little scaling and decarbonization occurs in recrystallization annealing, it is preferred over full annealing. No phase changes takes place and this final structure consists of strain-free, equiaxed grains of fine ferrite produced at expenses of deformed elongated ferrite grains. However, it would produce very coarse grain if the steel has undergone critical amount of deformation. In such cases, full annealing is preferred. Aim of recrystallization annealing: to restore ductility, to refine coarse grain, to improve electrical and magnetic properties in grain ordered steel. This is a typical recrystallization curve to constant temperature. Timing of annealing and percentage of recrystallization varies by incubation period. Now we are seeing spheroidized annealing. Spheroidization annealing consists of heating, soaking and cooling invariably very slowly to produce spheroidized perlite or globular form of carbide in steel. To improve the machinability of annealed hypoelectric steel, spheroidized annealing is applied. Hypoelectric steel consists of perlite and cementite. The cementite forms a brittle network around the perlite. This presents difficulty in machining the hypoelectric steel. The process will produce a spheroidized or globular form of a carbide in a ferritic matrix, which makes a machining easy. Prolonged time at an elevated temperature which completely breaks up the perlitic structure and cementite network. The structure is called spheroid. Here we can able to see the structure of the spheroidized process applied at a temperature below and above the lower critical temperature. Now we are seeing spheroidized process. Heating the part to a temperature just below the ferrite austenite line A1 or below the austenite cementite line, essentially below the 720 degrees centigrade line. Hold the temperature for a prolonged time and followed by fairly slow cooling. Cycle multiple times between temperatures slightly above and slightly below the 720 degrees centigrade line. For example, 700 to 750 degrees centigrade. Slow cooling. For tool and alloy steels, heated to 750 to 800 degree and holding for several hours, followed by slow cooling. This is a chemical microstructure of the spheroid. All these methods results in a structure in which all the cementite is in the form of small global spheroidized disbands throughout the ferrite matrix. This structure allows for improved machining in continuous cutting operations such as lathe and screw machines. Spheroidized also improves resistance to abrasion. Aim of spheroidized annealing: minimum hardness, maximum ductility, maximum machinability, maximum soften. That's all for today. Thanks for listening the session. Thank you.